Good morning, depending on when you're watching this, good afternoon, good evening, or good night. I'm your Calc 1 instructor, and today we're going to be starting Chapter 4, Applications of Derivatives. Now I know what you're thinking. Didn't we just go through several sections dedicated to applications of derivatives? Section 3.7, Rates of Change in Science. Section 3.8, Exponential Growth and Decay. And Section 3.9, Related Rates. In all these sections, we used derivatives to answer real-world problems. However, we missed what is quite arguably the most important application of differentiation: optimization. I want to maximize the acceleration of my car. I want to minimize the cost of manufacturing some good. I want to maximize the area I can enclose in a fence. If I can express these quantities as functions, then I can use calculus to optimize them. How exactly we do that is going to be the goal of this chapter. We will illustrate with a simple example using a problem from the last exam. A rock is thrown vertically upward from the surface of Mars with an initial velocity of 15 meters per second, so that its height after t seconds is h of t equals 15t minus 1.86 t squared. But if we want to find the maximum height achieved by the rock? In other words, what time maximizes the rock's height? Let's think about this physically. What can you say about the rock when it's at its apex? Can you say anything about its velocity? What can you say about the velocity of the rock as it's going up? Going down? The velocity of the rock is positive on its way up. Its height is increasing. Similarly, velocity is negative going down. So what do you think the velocity of the rock is when the rock is at its maximum height? 0. At this point, the velocity of the rock changes from positive to negative. So we can guess that it must, at this point, be 0. You can see this for yourself if you grab any small object and carefully toss it into the air. The speed of the object slows down as it reaches its apex, even appearing to be still for a moment, then speeds up again as it falls back down. This matches up with the graph of h of t as well. We see that there is a horizontal tangent line at its highest point on the graph, so the derivative is 0 there. Therefore, to find the maximum height of the rock, we want to find h of t at the time when v of t equals 0. So we start by solving v of t equals 0. Recall that v of t is equal to h prime of t, the derivative of the height function with respect to time. So this is just 15 minus 3.72 t. Thus, v of t equals 0 precisely when t equals 125 over 31, or approximately 4.032 seconds. Therefore, the maximum height of the rock is h of 125 over 31, or just approximately 30.2419 meters. This method of optimizing, of setting the derivative equal to 0, is one we will elaborate and generalize throughout this chapter. First, we will clarify this. What do we mean mathematically when we speak of maximum and minimum values? Tune in next time. Same math time, same math channel.